Alright, last one here. Sample of carbon dioxide is contained in a 5 liter, so there's our volume, with a pressure of and a temperature of. What will the pressure be? So we're looking for a new pressure. If the temperature inside the 5 liter tank, there's our volume, is raised to, and there's our temp. Now take a look at this. The volume is 5.0, and it's still 5.0. The volume doesn't change, so guess what? You don't need it. All you have to worry about is P and T. So you look at the equation, PV equals nRT. The only things that change are your P and your T. You don't need volume because it doesn't change. You don't need N or R. Divide through by T to get this on the left, and then we end up with P over T. So it's P over T equals P over T, 1, 1, 2, 2. So here we go, plug them in. We got 750 on top, millimeters mercury. Temperature is already in Kelvin, that's nice. We don't have to do any conversions. Over here, new pressure is going to be X. New temperature is 310. Solve for X. P2 is going to be 801.7 millimeters mercury. And I know it's millimeters mercury because that's what the other pressure value is measured in right here, this 750. Alright, 51 is basically a Dalton's law problem. So it says that air consists of 78.1% nitrogen, it gives you the carbon dioxide and gives you the trace gases, and then it says in addition to oxygen, so oxygen's also in there. And it basically asks you to figure out the percent of air that consists of oxygen. So you know the whole thing is going to equal 100%. You know that all the air is made up of nitrogen plus CO2, put an N2 there, it's diatomic. Trace, so we'll write in the word trace, which is a bunch of other gases in small amounts, and oxygen. So those are all our components that make up air, and it makes up the 100% of air. So now what parts are we given? Well, we know that nitrogen makes up 78.1% out of that 100. We know carbon dioxide 0.04% of that 100. We know trace are almost a percent, 0.93%, and oxygen is missing. We don't know. So this looks to me like it's a simple subtraction. 100% minus this, minus this, minus this. Solve for X. And X is going to be 20.9, just about 21% for oxygen. Alright, now we've learned all of these wonderful calculations. We've learned all these things about gases and how they're supposed to behave. However, there's something you need to keep in mind. Gases normally do follow those rules. They do act as this wonderful ideal model that we've learned about. But there are instances where real true gases stop following those rules. So we learn the difference between an ideal gas and a real gas. Now, ideal is kind of this wonderful idea that we have about what gases should do. And normally real gases do follow along, but sometimes they deviate from that model that we have. The two conditions that you need to know are low temps and high pressures. Think about what happens at low temps. Think about gas particles zipping around when you take a shower. You got hot, happy gas particles. Do they always stay hot, happy gas particles? Theoretically, if you reduce the temperature, if temp goes down, then the pressure and the volume should also go down. Down, 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 until theoretically it hits absolute zero. Is that really going to happen with the water vapor in the air? Or is it just going to condense when it gets cold enough and stop playing along, stop being a gas? And that's exactly what happens. One of the assumptions is that there's no interaction between the particles, no intermolecular forces. Well, normally there isn't, but if you cool them down close enough, then or slow enough rather, then that force becomes important and they do start attracting to each other and forming a liquid. Same thing with high pressure. Normally, you should be able to squish, squish, squish gases, get them closer, closer, closer together until the volume is nothing, in theory. But obviously gases don't follow those rules to the extremes. When you push them close enough or force them close enough together, those actual particles start interacting with each other and taking up space, and now there's a limit to how close you can get them. They can only go so far. So at high pressures, when they get close enough, they also condense. They stop playing along, they stop being a gas.